Hey, Algebra 2, welcome back. Here's our last video for Chapter 7. I think I misspoke in the last video. I think I said that was the last video for Chapter 7, but this one is the last one. I was thinking ahead. I was just so excited to move on. But here's our last topic for this chapter before we kind of, checkpoint it up next week and then move on to better things, okay? So we're solving exponential equations here, and so that's pretty much our objective, is to solve exponential equations by either relating the bases, we'll talk about what that means here in a little bit, it's kind of one of our methods, or by using our previous log knowledge that we've acquired from 7.4 and 7.5, okay? So in yesterday's video in 7.6a, we talked about how the logarithmic function is something called one-to-one, right? So we talked about how that, let me go ahead and write that down, is one-to-one. And what did that mean? Like, what was the significance of that? Well, the significance was that if I had log base b of x is equal to log base b of y, then I could say that x is equal to y because of the fact that one-to-one means not only for every x, there's only one y assigned to it, for every y, there's only one x assigned to it. So if the outputs are the same, then the x values, the inputs, have to also be the same, okay? And that helped us to solve a bunch of log equations. Okay, well, thankfully, the exponential function is actually has the same characteristic. The exponential function is also one-to-one. Okay, very convenient for us. Okay, and so what does that mean for exponential land? Well, if I have some base b to the power of x, and so that's equal to some base b to the power of y, well then, just like in our log function, x is equal to y in exponential land, okay? If the outputs are equal to each other, then the inputs also have to be equal to each other, okay? That's the idea behind one-to-one, okay? And so that's going to help us with solving certain exponential equations, okay? And that's going to help us with this idea of relating the bases. So let's talk about what relating the bases means, okay? Relating the bases. Okay, when I am asked to solve an exponential equation using this method, what usually happens is we have an exponential on each side of the equation, okay? So first thing is that there's an exponential on each side of the equation. And so what does that mean? Let me actually get rid of this little caret mark. So try to make bases the same. Okay, because then what happens if we make the bases the same? Then we can just set the exponents equal to each other like we've done in the log function land. And then from there, it was always kind of simple. We could always get x by itself from there, okay? So let's practice what that means. Let's see what we can do in terms of relating the bases and using this one-to-one idea, okay? So solve the following exponential. Exponential. There we go. That's a lot better. Solve the following exponential equations. Okay, so we're going to try using this relating the bases method. Okay, so looking at A, 9 to the 2x, 9 to the power of 2x is equal to 27 to the power of x minus 1. Okay, so our goal is to get the bases the same. I want these two bases to be equal to each other. Okay, how can I rewrite them so that they're the same base using my knowledge of exponents, right? Well, I know 9 is a power of 3, and so is 27, actually, right? 9 is equal to 3 squared, and 27 is equal to 3 to the third power. I can use this knowledge to my advantage, and notice how 3, those are the same bases right there. So if I rewrite 9 and 27 in this form, then I can achieve that goal of getting the same base on each side. So on the left-hand side, instead of writing 9 in parentheses, I'm going to do 3 squared to replace that 9. Here's where 9 should be. And so then that's still to the power of 2x, because this is 9. is equal to, same thing here, instead of writing 27, I'm going to write 3 to the third power, replacing that 27, and then still to the power of x minus 1. Okay? And so now I need to kind of clean this up a little bit so that I can then use the one-to-one property. Remember, when it's exponent to an exponent, those get multiplied. So 2 times 2x, that's going to be 3 to the power of 4x. And then 3 times x minus 1, that's going to be 3x minus 3. Okay, so there is our equation with the same base. We've related the bases. Our bases are now equal. So now what I can do is set the inputs, the exponents, equal to each other. Okay, here is my b to the x equals b to the y. So now I can write x is equal to y. Okay, set the exponents equal. And you can't do this unless you have the same base on both sides. Okay, and it has to be exponentials on both sides. If this was 3 to the 4x was equal to just 3x minus 3, I would not be able to do anything here. Okay, I would not be able to do this nor just anything else in general. Okay, so then now I just solve for x. So subtract our 3x over. I get x is equal to negative 3. And we're all done, right? With logarithms, we got to look for extraneous solutions. Here, we don't have to. Let's think about why. When we had to do extraneous solutions for logarithms, that's because our domain was restricted to just positive numbers. So I have to make sure and go back and check to see if I get any log of negatives, right? Here, I don't have that issue with exponentials because the domain of every single exponential function is all real numbers, negative infinity to infinity. So I don't have to worry about plugging this back in. I mean, you should still plug it back in to make sure that it is the right answer, but I don't have to worry about knocking out any extraneous solutions because there won't be any, right? The only time I get extraneous solutions is when those solutions are not in the domain of the problem. Okay, so we're good. We can move on. B, same idea. 4 to the power of x is equal to 1/2 to the power of x minus 3. So looking at 4 and 1/2, okay, notice that we can write both of those as powers of 2, okay? 4 is equal to 2 squared, right? And then 1/2 is equal to 2 to the negative 1. And so just like I did over here, same idea here. This 4 becomes a 2 squared, but then still to the power of x is equal to 2 to the negative 1, but then still to the power of x minus 3. And then I proceed just like I did over here. 2 times x is 2x. Negative 1 times x minus 3 is negative x plus 3. Now I can set my exponents equal to each other. 2x is equal to negative x plus 3. And then I solve. I add over this x. I get 3x is equal to 3. And so x is equal to 1 once I divide over the 3. And we're all set. Okay, really great technique to use. Not always the case that I can use it though. Okay, and so sometimes we can't relate the base. Okay, so that's going to be a good little note to write. Sometimes can't relate the base. So we use logs in those cases. Okay, if I can't relate the base, for example, let's maybe think about like 5x to the power of 10, and we're trying to solve for x. Okay, 10 is not a power of 5. It's a multiple, it's 2 times 5, but it's not a power of 5, not a nice power, right? And so I won't be able to relate the bases here because there's no way I can write 10 as a power of 5. And so I can't really relate the bases there. So I need to use logs in that case instead. Okay, in those cases, okay, important note, in these cases, always isolate, so get by itself, isolate the exponential. Okay, so spoiler alert, in these cases, you're actually only going to see one exponential. In these cases up here, we saw an exponential on each side. In these cases where you won't be able to relate the bases, you're only going to have one exponential on one side, okay? So always always isolate the exponential first before using the log, okay? So let's see what that means. Okay, example 2, solve the following exponential equations, round to 3 decimal places when necessary. So for the first one, 4 to the power of x equals 11. Notice how our exponential is already by itself. There's nothing extra alongside with it. So I'm good. So what I'm going to do here is I'm going to think ahead, and I want to use one of my properties of the logarithms, okay? The one that I'm referring to is the one that says log base b of m to the power of n is equal to n times the log base b of m. Why this one? Why do we care about this property? Well, if you notice, this property gets exponents down from the exponent, right? If there's something in the exponent, I can easily bring that down by taking a log of that thing, okay? And that really does help us here because why? Notice what's in the exponent in part A? The x, the thing that we're trying to solve for. So if I take a logarithm of both sides, then I can bring that x down and now I can solve for it, okay? So what we're gonna do is we're either gonna do a log base 10 or a natural log because we're gonna get something that we need to punch into our calculator. And we can't do it unless it's a log base 10 or a natural log. So here, let's just use a log. So take log of both sides. So log of 4 to the power of x is equal to log of 11. Okay, so what can I do here now? Well, now I can use that property to bring down my x to the front. I get x times log of 4 is equal to log 11. Oh, great. What does that mean for me? I can solve for x. Log of 4 is a number that you can put into, it results in a number, right? Log of 4 is some number. And so here it's like I have 2x. How do I get rid of the 2? By dividing both sides. So here, divide both sides by log of 4. Okay, so my answer is going to be whatever I get from putting log 11 divided by log of 4 in my calculator. Okay, so do that really quick in your calculator. Let's see what we get. Okay, I had to pull mine out really quick. Log of 11 divided by log of 4. All right, we get an answer of about 1.7297. So that actually becomes 730 since we're rounding the 3 decimal places. Cool, so there's our answer. 1.730 is our x value. 4 to approximately this power gives us 11. Awesome. All right, let's try that again in part B. 7 to the power of 9x equals 15. My exponential is isolated. There's something extra in the exponent, but we'll get there, right? All I know is that I need to bring this exponent down to the front. So we do the same thing. We take the log or the natural log of both sides. Let's do natural log this time. Natural log of 7 to the power of 9x is equal to natural log of 15. I can use my power property to bring this 9x to the front. So I get 9x times natural log of 7 is equal to natural log of 15. Now I notice that here I have 9 times x times natural log of 7. So just because we're lazy, we can in one step divide by both 9 natural log of 7 because I get rid of the 9 and the natural log of 7 on that side. And so here's what I have. So x is going to be natural log of 15 divided by 9 times natural log of 7. Okay, and let's see what we get from that in our calculators. All right, I would put that 9 natural log of 7 in parentheses just in case your calculator doesn't do that order of operations correctly. So natural log of 15 divided by parentheses 9 natural log of 7, close parentheses twice. Okay, we end up getting that x is equal to 0.155. Okay, so there's our answer for that one. Last but not least, for e to the negative 0.3x minus 7 equals 13. here's where it's important that we isolate the exponential. Okay, what's our exponential? It's just this e to the negative 0.3x. It's the base to the exponent. So I need to get rid of this 4 and this negative 7. Let's start with the negative 7. We can add that to both sides. I get 4e to the negative 0.3x is equal to 20. Then the next thing I can do is divide both sides by 4. I get e to the negative 0.3x is equal to 5. And now here I have exponential equals a number. Okay, now I've said you can do either log or natural log, but here it's going to be really advantageous of us to use the natural log. Why? Because natural log has a base e. Here we have base e exponential. So let's see why it's a little bit advantageous for us. So take the natural log of both sides. I get natural log of e to the negative 0.3x is equal to natural log of 5. Okay, I can take this exponent and break it down to the front. I get negative 0.3x times natural log of e is equal to natural log of 5. What is the natural log of e? Okay, well, if you're ever in doubt, how do we evaluate a logarithm? What's the base here? E. E to what power is equal to e? E to what power is equal to itself? It's just 1. This is equal to 1, right? So I have negative 0.3x times 1. This is just 1. So then all I have here on the left now is just negative 0.3x, because anything times 1 is itself. Ah, okay, so now all I have to do is divide both sides by negative 0.3. So x is equal to natural log of 5 divided by negative 0.3. Okay, go ahead and put that in your calculator. What is that going to give us? Okay, we get an answer of negative 5.365. Awesome. Okay, so there you have it. We solved a few different kinds of exponential equations. Ones where we related the base, we did not need any sort of logarithm. And then ones where we did have to use a little bit of logarithms, okay, where the bases cannot be related, okay? And that's kind of what it boils down to. If you can relate the bases, then relate the bases. And if you can't, then you will need to use logarithms, okay? All right, you guys, see you next time. Have a good rest of your day.